Welcome to everybody. I'm delighted to be here again. This is always a high point of the year to talk about this subject. The point of interest in nanotechnology is that it's something one hears a lot about, and you are in the business of talking about this subject to people who are interested in or not interested in science. And a good question is it something which they should pay attention to? Is it something you should pay attention to? Why is it interesting? What is it? And I want to try to give you a quick run through a lot of stuff to give you enough of a feeling for the landscape that you know where Nano is situated in phase space and generally what its parts are. How many wings does it have? How many legs does it have? What color is it? It's that kind of thing. And I'm sure there's going to be lots of room to talk about it further as you progress onward during the day. So the three topics are these three. The obvious one is, what is it? And the answer to that is not entirely clear. Of course, it's small things, but small means what, and why does anyone care? Second issue is, why is it interesting? And 5 years ago, 10 years ago, when the area first emerged, the answer to that question was not at all clear. It's now getting to be pretty clear. I think we can say where Nano is going to make a difference and why. So at least there's a point of focus for the discussions. And then the final issue is it really going to be something that changes the world, and is this a good thing or a bad thing? It is regardless of its character for a variety of reasons, which we'll talk about. And the better or worse is a good thing to talk about with students. So let me give you an idea of what some of the major scientific and technological themes are. The one that is certainly making the biggest impact in the shortest period of time is electronics. And people say, will there be a nanoelectronics? The answer is there already is a nanoelectronics. I mean, it's already a big deal. It has happened. It will continue to happen. And its consequences are enormous, enormous for the world, not necessarily strictly as a result of nano. I mean, it's electronics that makes the difference, but nano is going to be a part of it, and the key part of it to pay attention to is memory, because information is going to be free. Materials, materials is stuff. It's the floor and the clothes, and I could knock gently on your head, but we're all materials. Anything that you can put your hands on. Materials make up the world. Nano makes up materials, and so there are many, many different contributions of nanoscience in this area. The question is, what are the applications going to be? Functional structures. It is my belief, which time will tell whether it's correct or not, that the biggest area for nano is probably going to be on the area of what I'll call commodity infrastructure, which is production of energy, production of water, the things that go into maintaining the flow of these major commodities that are responsible for environmental maintenance and things of that kind. It's already an important part of these areas, but it's becoming rational, and we'll chat about that as we go on. Everyone's interested in medicine. The answer in medicine right now is not clear. It's not clear that it's going to be a revolution. It's certainly going to be an important contribution. And then, of course, one of the big areas of interest is research, because what nano is enabling us to do for the first time is to see the world, the physical world, at a resolution and a scale that's been impossible in the past. So you add those up, and it's a big deal. Lots of interesting stuff. Now, I think it's always a good idea to think about why people do something. And this actually varies a lot from area to area of science. Why, for example, did nuclear energy emerge? And the answer to that is, to be pretty bloody-minded about it, that we in the Soviet Union were in a race for nuclear weapons. And out of that came power and things of that kind. But that was a technology that was fundamentally weapons-driven, national defense-driven. This area, I think, nano is a little bit more in the order of this. It's exploration. But exploration has a little bit the sense of we set off with pure hearts to explore the new world. Actually, nobody goes off to see if there's an edge of the world that they can drive over, or if it's possible to find a sea dragon that will eat the boat that you're on. That you just don't do that. You do it for another reason. And Columbus, when he went off, it was a mixture of probably some desire to get out of town, get away from his wife, some interest in making money, some interest in gaining stature in the court. I suspect he was testosterone poisoned, as many people are who are explorers. You know, there are lots of reasons for this, but it was not just pure science. It was a mixture of science, aggression, status seeking, profit, whatever. And that's the same thing here. It's a whole mixture of stuff, and all of them are mixed up in an interesting and neat way. But one of the acronyms I remember and try to operate by is WASP leg. And WASP leg is wrath, avarice, sloth, pride, lust, envy, gluttony. Those are the 7 deadly sins. And I think it's good to remember them and then also arguably to practice them, because they provide such good motivation for much of the world. Let's start with dimensions. There are a couple of different ways of thinking about nano. A nanometer, how big is a nanometer? A micron, let's start with a hair. A hair is 100 microns. A nanometer is 1,000th of a micron, so a nanometer is 100,000th of a hair. Hairs come in different sizes. Some hairs are more evident than other hairs. But the smallest thing that you can see with most eyes is about the diameter of a hair. And it's 100 microns. It's about the limit of visibility. So go down by 100,000, and what you get to are things that are the size of molecules, and that's a nanometer. So a typical molecule is about a nanometer in size. And these are the sorts of analogies. This is one which I find useful. If you think about my favorite mountain, which is Denali, because it sits on a plane that's quite low here. You see the entire mountain. The ratio of that to that is 10 million, and the ratio of a baby's finger to a molecule is about 10 million. So it's small. And here's the scale that you've seen on many occasions. That's a hair at 100 microns. Spores for pollen are down somewhere around 10. Red blood cells are perhaps 3 microns. Viruses are down around 100 nanometers. Molecules are down around a nanometer. And the reason why, in terms of science, this area has been so interesting is that there's a region down here with molecules, which is what chemistry has done. It makes molecules, and we actually have a pretty good sense of a lot of that. And then there's a region up here which one can see microscopically, and which has also been the region that people make things top down. They fabricate circuits and do things of that sort in that scale. And the region in between, down in here, for a variety of reasons, has been difficult to look at, difficult to manipulate, difficult to access, so that people didn't really know what was here very clearly. And it's a reason to be particularly interested in that intermediate stage. It's not that it's the smallest thing around, it's between what you can do from the top down in size, from large scales going to smaller, and from what you can do from bottom up, which is little molecules going to bigger molecules. So, what is it? We tend to think of the area in terms of structure. So the definition, the current definition of nano is that it's less than 100 nanometers. Really, it's less than about 50 nanometers. So 50 small molecules lined up end to end. Or if you want to think about it in terms of atoms, a gold atom is half a nanometer in size. So 50 nanometers is 100 gold atoms in a line. So that's a good dimension. Synthetically, we've said top down to bottom up. The part that's more interesting is functionally. And the world is basically constructed on function. You know, you don't ask what is it, you ask what does it do, and that's the function. And so there are 2 sets of things here that are functional. One is that there are a series of uses in catalysts, in pores, in membranes, in memories, and a bunch of other things which we'll talk about. And then there's also another issue which has just begun to be exploited, which is that philosophically one of the most interesting things about the world to me is that I am made up of atoms, you are made up of atoms, which are quantum objects, and you are a classical Newtonian object. So if I drop you, you go splat, I understand that. If I take an atom and I send it at the wall, it can go through it, which you can't go. So what happens in between? How does something that's a collection of quantum objects which we cannot understand become a classical object? And that transition occurs in this region of nanometer scale stuff. So if you're interested in the subject of what is the nature of what we loosely call reality, this is the area that you'd like to look at carefully. Now, there are also a couple of other interesting issues from your point of view. One of them is that nano is not fresh bread. That is to say, it's not the answer to everything. I'll show you what I mean by that in just a moment. Often what we're concerned with is small, because small brings portability, it brings low reagent costs, it brings high speed, it brings all sorts of other characteristics. And then also from the point of view of public understanding, people don't know the difference between nano and micro and submicro. You know, all that stuff is not important. Either you can see it or you can't see it, basically. And so what one is concerned with are things that are small enough that you can't see them and you can get a lot of them in a small space. That's basically the issue. So atoms are very, very small, and nanometer scale structures are sort of small, and micro is just barely small, but that's all distinctions. Here are just examples of what I mean by different scales of small. This is a true nanostructure. This is a ring of gold, and the walls of this ring are 40 nanometers. That's 80 gold atoms across. And it's a kind of circular structure, and you say that's sort of neat. What's it good for? And the answer is I have no clue, you know, which sort of symbolizes nano. This is one of the things that will change your life. This is a prototype of a radio frequency ID tag. It's a passive device in which you have an antenna, and then there's some little structures down there in the middle. And the reason why it's interesting is that it's passive. These are going to be used in the following way. You go to the supermarket, and right now we have a human interaction still in the supermarket. You buy a head of cauliflower, and you talk to the supermarket clerk who's in a good humor or a bad humor. With this, the head of cauliflower has one of these little tags on the bottom, and as you leave, you go through a portal, like the portal at the airport, and the portal will read, it talks to this, and it says, what were you? And it says, I'm a head of cauliflower. And where were you? And I was on the second shelf to the left on aisle 3. What kind of cauliflower were you? What size cauliflower were you? All this information gets passed back and forth. And by the way, your bank account is debited in 10 to the minus 3 seconds after this transaction has occurred. So you eliminate all human contact at the supermarket, and if you happen to fall in the marginal Asperger's class that most of us do who are basically physical scientists, that's not a bad thing, but if you're otherwise human, it's problematic. So this is an example of something that's a big deal because it's part of a transition in medium scale from a world in which we're all separate to something in which everything is connected. Your shoes talk to the wall talks to you, you talk to the lighting, all of it without active participation on your part. This is a top view of something which is, you see there's a dime and there's the size of the object. These are all little channels that happen there to be filled with dye. And that's going to be used to make a chip, a little fluidic chip, in which the fluid that runs around in the channels are not electrons, as in a microelectronic device, but are used to make a fluorine-18 radioactively labeled compound. Well, why is that interesting? It's interesting for an application called PET, or positron emission tomography. And positron emission tomography is something in which you can see molecules connecting to receptors in vivo. So it's potentially interesting in looking at, let's say, where the tumor is on your liver. Is the resolution good? No, the resolution is atrocious. On the other hand, the idea in this is that what one is going to do is to take X-ray pictures, which have very, very high spatial resolution and very low chemical resolution, and combine it with this technique, which has very low spatial resolution but very high chemical resolution, to provide a wonderful picture of where the tumor is on your liver. Now, I don't know whether that's going to be helpful to you or not. However, GE paid for a company that does something of this sort, paid $7 billion a year or so ago, which gives you the impression that GE thinks it's going to be terrific. So capitalism being what it is, you can draw your own conclusions about that. But here you're working with things of the size of hairs. Here you're working with things that are just, I mean, after all, this entire thing from here to here is 1/100th of a hair, and then this is even bigger than that. So they're different sizes for different purposes. Okay, historically, why is it that you've heard about nano but haven't heard about quantum optics or haven't heard about some of the other things that go on? There are a whole series of really interesting opportunities at any time in science and technology something to emerge as the Celine Dion of the world of physical science. Just think about some of the ones. My personal bet is the one that's going to change the world in the next period of time is intelligent machines. Because in the great competitions between the developed world and the developing world, the big difference is basically cost of labor. We can never compete on that basis, so what we will do is make machines that eliminate labor with unusual consequences for the future. But there are a lot of other interesting things here, and sustainable is certainly an interesting one. Why is that not the same buzz? It's actually getting there, but not been the case. Technology for globalization, soft robotics, whatever it might be. How is it that nano emerged as the flavor of the moment, and what's the background for this? Is it a unique opportunity? Well, no. The reason it emerged is a complex set of parameters, which in combination have set off this interest. The first idea is something which was basically, how do I put this really politically correctly and politely, it was nonsense, which was the original idea of little anti-cancer submarines. There was a notion that you could take the machines that we see in the world and simply make them smaller and smaller and smaller, and then you put them in the bloodstream and they go and find cancer cells, or the one that people worried about was something called the assembler, which was supposed to be like a little robot that would pick atoms out of the environment, make more of itself, and expand exponentially. Just total nonsense. But sort of neat nonsense. So everybody likes to go to bed with this little frisson of terror going down their back, so long as they don't really believe it's true. That was called Grey Goo. That caught the attention. There's some very real opportunities here. The science, as in automobiles, selling, as in teaching, as in anything, is always a mélange of self-advertisement and reality and accomplishment and promise and whatever. The ratio of hyperbole to reality here has been, it gives you great confidence in the species. The enthusiasm sometimes exceeded the reality. Science politics, one of the issues here was that there is a general appreciation, if you're in the world of science policy, that the United States allocates too many resources, too large a fraction of its resources to public health. What's changed the world in the last period of time has not been genomics, it has been information. I mean, our world has been rewired by the internet. It hasn't been rewired by the genome, but most of the money has gone into the genome in the last period of time. So how does one correct that in a political world? And the answer is you find some part of the politics in which all the sciences can get together, and that's turned out to be nano. There are some really big deals in terms of technology, which we'll come to, and then not a small thing is that one of the areas that makes things happen in the United States is the venture capital world. And the venture capital world was looking for a what's called new thing at the time that nano was first emerging, and so it picked on nano as being an interesting subject. And in venture capital, you don't really care how things work out in a certain sense so long as there's a lot of stirring of the pot. Okay, so I want to organize the discussion of the subject in terms of 6 ideas, 3 in science and 3 in technology. I'm going to pass very briefly over this issue of quantum phenomena, but I want to make it evident that this is part of the story. The ability for the first time to look at single atoms and molecules, to actually see them. And I'm a chemist by background, and it is remarkable that my entire career was spent talking about atoms and molecules, although I've never seen a molecule. I mean, I infer it's there, but I've never actually seen one. For the first time, it's possible to see them. A whole bunch of neat things in terms of the cell and biology. And then the technologies are, the dominating one is information. The one that is probably the newest at the moment is materials. And then what I think is going to end up being the biggest deal is energy, water, the environment, sustainability, and so on. Those are the ones that are going to make a big difference. So that's the organization. Now let's start here. This is something you've all seen. It's just a prism. And in the prism and in diffraction is essentially everything you ever want to know about quantum mechanics. I mean, diffraction has it all. And in particular, it has, to me, one of the most unnerving equations in natural science, which is this one, which is very interesting. I'm a teacher, you're a teacher. I suspect you have the same problem that I do, which is it is sometimes very difficult to get students to appreciate that an equation is telling you something. You know, it's not just a black box in which you drop pennies and something comes out at the end. To me, an equation is very much like poetry. And what it is a description of reality in a form that we can't otherwise really describe. This one says that for electrons or things of that sort, that the wavelength of the electron, we'll say, is related to mass and velocity, that is the momentum. The thing that's amazing about this is wavelength, this is wave, and momentum, that is particle. And so that's an expression of the wave-particle duality. And if you stop and think about it, not just as a simple equation, but as a statement of reality, it really does send shivers up and down your spine. Now, the last time I used this slide was for a course that I'm giving. And I used different poems, and I'm sorry I forgot to really change it. The poem I much prefer is one by Margaret Atwood, which I will now recite for you. It's politically incorrect in the course of a course. The poem is 4 lines. It is, "You fit into me like a hook into an eye." Beautiful Margaret Atwood erotic image. A fish hook, an open eye. Margaret Atwood is not terribly fond of men, I think. But that's an expression of reality in a very economical way. This and this are, you know, they're the same kind of thing. We just need to think about it. But this gets into the issue of why is it that if I take an electron and flick it at the wall, it goes through, if I do it the right way. And if I take you and you flick you into the wall, you're really very, very annoyed because whatever happens, you don't go through the wall. And when you and I discuss it afterwards, I'm likely to lose teeth. And if any of you would like to discuss the nature of reality as it is, it's one of my favorite subjects. It really is extraordinarily interesting. All right, single atoms and molecules. Here the issue is an idea that before was really very unexpected. And that is when we see something, you know, to see means photons and eyes. Basically, that's the idea. And the question is, when you go to something that's very small, small enough that diffraction tells you that you can't see it, how do you see it? And the answer that turned out to be the right answer, and a little bit unexpectedly, was you feel it. And of course, the reason for that is that if I feel something, the uncertainty in the contact of surfaces is in the order of the van der Waals interaction. It's the size of an atom, which means really 1/10 of an angstrom or something like that. There's no uncertainty down to that point. With light, there's an uncertainty at hundreds of nanometers. So it turns out that the way that you see, in quotes, atoms and molecules is by various devices that are basically fingers of one or another kind. And the classic atomic force microscope is something in which I have a finger, and I bring the finger down and, you know, feel my wrist that way. As I try to bring this over, my arm has to rise up a little bit. And you can detect that motion, the motion of a finger here, feeling a surface that has atom-sized bumps on it by watching tiny deflections in this arm, the cantilever arm, in a device of this sort. So there's the sample. Here's the cantilever, which with the finger that feels things, you shine light from a laser down on this. It reflects into a position-sensitive detector, and you can detect changes in that position of, you know, easily 1/10 of an angstrom by watching where the beam is deflected over there. So here is a real picture of what one sees here. This is from Don Eigler, and it's a kind of poster child for this area. Each of those things that you see is an iron atom on a copper surface. So you're really seeing atoms.
I'm so happy to see them, I know they exist for the first time. And then what you often see is a picture of this sort, and it's a representation of what this is supposed to be, but this is what you really see. An atom, of course, doesn't look like an ice cream cone. An atom is a sphere, but if I try to bring a probe over that, the probe will make a kind of inverted pyramid shape. It can't feel underneath the sphere. So that's why these things have a kind of ice cream cone shape. This series of ripples in the background is just like water in the bathtub. It is fundamentally ripples in the electron sea, the sea of electrons that's in the surface. And what you're seeing here, if you see a point there and a point there, that's exactly the same thing as the Whispering Gallery in Washington when you take the kids down to see that. You stand here and the sound is reflected to there, and there's a standing wave in the electrons. So the phenomena are basically very much the same. If you understand, if the kids understand these simple things of how electrons move around atoms, it turns out that you can construct the periodic table in a way that makes perfect sense. The periodic table is just the hydrogen atom and the quantum mechanics of that being worked out. And here's what a finger actually looks like. Here's a tip, and then this particular finger has a long projection, which is a carbon nanotube. That's 10 nanometers, so this is about 2 nanometers across, means 4 gold atoms. And the carbon nanotubes are so strong that they actually are freestanding at that kind of dimension. So imagine that 4 atoms across and feeling the surface with it. It's really amazing that it works as well as it does. The cell, biology, and biomedicine. The way I think about this issue is the following. That in biology, what one is fundamentally interested in is the cell because it's the smallest thing that's alive. You're interested in life in biology because biology is basically the study of life. That's terrific. If you're interested in medicine, you'd like to know how cells connect to things like hearts and brains and livers. But a biologist is fundamentally interested in this. Now, this object is made up of proteins and lipids and carbohydrates and whatever, molecules. And the amazing thing about life, and one of the great questions in modern natural science, is how do you go from molecules and reactions, which are molecules and reactions, to the cell, which is alive. Something happens in between here. You know, things become alive. And there's a very, very interesting series of subjects which stem around the fact that we have 2 words. We have alive and dead, or alive and not alive. But are those the only possibilities? I mean, how about something that's not quite alive, or a little bit alive, or alive but not alive? I mean, the fact that we have 2 words doesn't mean that that's the way it is. And there's probably a continuum between alive and dead. So, for example, better to take me. Take me. Soon I die. And I don't die all at once. It isn't the bulb goes out, brain begins to cease to function, but my hair, if I had hair, would continue to grow for days afterwards. So parts of me are alive and parts of me are not alive. But even the parts that are alive are probably chemical reactions that are just sort of going on for a while. And this question comes up in a very, very interesting way when you ask, how did it get started? You know, what's the origin of life? Because life, as far as we understand now, came out of a pea soup of reactions in some ghastly primordial planet. And out of that came this, and Beethoven somehow. We don't know how any of that happened. Anyway, the point of interest is that if you want to look at this, which is a couple of microns across, you need probes that can look at small parts of it. So if you look at the cell in greater detail, here's a cutaway, a schematic, and there's the nucleus down in there and the Golgi and mitochondria and various fibers and stuff like that. That's an electron microscope picture of the same kind of thing. And you need to be able to look at pieces like this. You need probes that are nanometer scale probes. So I want to just show you a couple of my favorite animals. This little fellow here is back here. He has a rotary motor that's churning around furiously, and then this exotic motion here consists of building structures internally that are fibers and then sort of pulling himself along. It really is the self-levitating elephant. And so he, she, it, they, whatever the right answer is, illustrates 2 kinds of motors. One is linear motor, which is the motor that makes your muscle run, and then a rotary motor, which is big for bacteria. And here's the structure of this, and it's truly astonishing. And it's related to another structure, which is, for those of you who are in the biology business, one of the most amazing things that I know. This is the ATPase that makes ATP in the cell. There's the lipid membrane here in schematic way. And here's a structure that sits in the membrane that rotates. And here's a shaft with various things attached here. Here's a kind of catch that catches as it goes around. And then as protons from the outside stream down into this structure, make it rotate and flip out here, this entire business is driven in a circular fashion that causes changes in the conformation of these proteins down there, and that takes phosphate and ADP and makes ATP. Unbelievable structure. Here's another one of my favorite structures, which is mitosis. And this is a picture I can watch indefinitely. There are all the chromosomes. And here they all somehow get organized along structures that you can't see, the actin filaments, and lined up the right way and then yanked into two separate sets with the right coding of each, so that ideally you end up with the same set of chromosomes in mother cell and daughter cell. And then after that's happened, chunk, you form a membrane down the middle, and this all dissolves to start making proteins into the nucleus. Now, all of that stuff is going on at the scale of a few nanometers. Those are tens of nanometers across. They are hundreds of nanometers. So you need those kinds of small scales. And that's one of the things that's coming out of the current enthusiasm for nano, tools that enable you to look at structures on that size. Here's a biomedical application. These are particles of magnetite. These particular ones are about 20 nanometers across. They're very biocompatible. You inject them into the bloodstream. They don't escape from the vasculature, but they change the magnetic properties of the water in the blood. And in magnetic resonance imaging, you can light up the vasculature this way. So this is a picture for this patient of the circulating blood in the brain. And you can see that if you were looking for an aneurysm or a tumor or something like that, you'd love to have that kind of information. All right, now, this is an interjection, the nature of revolutions. We say that nano is revolutionary. What is revolutionary? That turns out to be a pretty interesting question, and one which people who are interested in the philosophy of science spend a lot of time futzing with. One way of thinking about this is to ask about some things that we would agree are revolutionary. The wheel is revolutionary, fire, bronze, whatever. And then at present, in terms of technologies, cell phones and radar and nuclear weapons, those have all been revolutionary in one or another fashion. The World Wide Web, and in the future, intelligent machines and highly sentient animals. Would you like to have a pet that is significantly brighter than you are? Would a pet that is significantly brighter than you are like to have you? Which is another more interesting question. But these are the kinds of things that technology raises. So where does nano fit in that? Well, here is an example of something that happened. This object replaced that object. And this object and that, the chip plus the fiber replaced, for better or worse, the letter. Although my wife points out to me that the fact that all email messages are essentially public, in her opinion, is going to bring back the love letter, because it's the only thing that you can do. A piece of paper is the only thing that you can write on that actually has some privacy associated with it. And here's the cell made up of objects of that sort, which are molecules. So which is it going to be? Is this going to be a really big deal comparable to that, or is it a little deal? We don't know the answer to that yet. There are, in the theory of revolutions, two kinds of revolutions. There's a revolution which is triggered by the invention of new tools. So the invention of the atomic force microscope, the scanning probe microscope, was a revolutionary tool because it enabled us for the first time to see individual atoms and molecules. Done. That's happened. So we have a revolutionary tool here. Inexplicable observations. There is a theory of revolution that says that science accepts revolutions only when it has to.
And so the question is, are we in a situation with Nano where we're forced to, and there are a number of parts of this, understanding how the cell works and understanding quantum phenomena and things of that kind, our back's up against the wall right now. We can't really understand what's going on. So I'm actually optimistic that for all of our torpor, this area is going to force us to rethink some things. All right, now back to some of the other subjects. Information, absolutely a big deal. When you think about information, it's good to think about it in a very broad sense. All of these are different forms of information. This is binary. That's, I don't recognize the tune, but anyway, that's musical notation. Here is information coded in the 4 bases of DNA, and then there's information just in the position of these atoms and lots of information in that. And in fact, the whole subject of information, for those of you who are interested in teaching students, it's very good to raise with them what the word means. Everybody knows what information is until you stop and actually ask yourself what information is. And since it basically is running the world now, it's not a bad thing to bring up as, what is information? And there's very elaborate and interesting theories constructed originally by a man named Shannon to understand that. Now, information is manipulated in the modern world in 2 ways. It's bits of electrons or pulses of electrons flowing around in semiconductor circuits, and then it's packets of light being transmitted through optical fibers from one place to another. So basically, most transmission now goes on optically in terms of fibers, and most processing goes on in terms of electrons in silicon. And the sizes that are permitted here are fixed by the sizes of the photons that are being transmitted. Here, the idea is that you can make things smaller and smaller. The basic way in which one makes silicon chips, I know is familiar to all of you. Photolithography, basically photography, that enables you to draw lines of different kinds in photoresist or on circuits, is the technology that's the underlying basis for microelectronics. And it is a technology that is right up there with bronze and the wheel. In fact, I would argue that it may be the most sophisticated technology the human race has ever invented. It's just phenomenal. And the entire of the information world is based on how that works. And it makes very small structures. And the underlying idea is that you do, as I say, photography with ultraviolet light. You shine light through a pattern. The pattern is then run through a lens, and the lens condenses that pattern into a small size, and various kinds of chemistry happen here that end up making a silicon chip. What's been so interesting about this is the supposition has been that the size that could be made this way was limited by diffraction. And it is, but you can tinker with diffraction. And so you use, if you, instead of shining the light through air, you shine it through water. That gives you a factor of 1.5 in size. You use shorter wavelengths of light, things get smaller. And one can now make structures commercially in which the lines are 40 nanometers at that point. And there's a roadmap that will get us, we think, to 20 nanometers. So this is a production transistor. The details are not important. What's important is simply that that feature size there is about 40 nanometers. So we'll go to half that pretty clearly in the next period of time. And then at that point, nobody knows what happens. I don't know whether we're going to go beyond it. But you know, physics tells you that you can't have a processor that's smaller than an atom, so we know there's an end at the end of this road. And how we get there is a little bit unclear, and how much money people are willing to spend to make things smaller is not quite clear. But when you think about this area, you should really think about that curve, because it's an interesting curve. This is the cost of a fabrication line. You know, we think about lithography in terms of making things smaller and smaller. Why do you want to make them smaller and smaller? Well, actually, you don't care whether they're smaller and smaller. What you care about is they're cheaper and cheaper. And so the whole idea is to make your device there cheap. You want to, well, it's heavy, but after all, your fingers are not going to get smaller and smaller. So at a certain point, that footprint is fixed. And so what you find here is that you can make things smaller. There are real disadvantages to make them smaller because you generate heat when you run a microprocessor. And if we took that thing and tuned it up to the highest speed it could run, right now, it would, running continuously, convert the temperature in the inside of the chip to about 1,000 degrees C and melt the silicon. that turns out to be bad for performance. Right. Expensive, right. Well, this is the real expensive. The factories to make these follow a curve of this sort, and the guess is that in about 2015, one of these factories will cost in the order of $100 billion. And I won't do the calculation for you, but if you want a 20% after-tax return on investment in a world in which the deepest moral value is return on investment, it's hard to do. You got to sell a lot of chips. And the number, which is a couple of years old now, but it still continues to astonish me. The number of transistors made in the United States now per second is, and there's a brief pause while you guess internally how many transistors might be made in the United States per second. But the answer is getting on probably toward about 10 billion per second. And you say, what do you do with 10 billion transistors per second? And I think you make lots of really smart toaster ovens. I don't really have a very good sense for that. But it's a lot of transistors. Transistors are really exceptionally stupid, I should say. All right, so now that's evolutionary stuff. That's happening, has nothing to do with the revolutions in nanotechnology. The revolutionary stuff would be to use carbon nanotubes and Bucky tubes and things like that, some completely new idea. Is that going to happen? My guess is no. But having said that, these are baby pictures, which are good ones to see. This is the first transistor. That actually was a paperclip. It's a little piece of germanium. That's less important than this sort of ghastly splotch, which is the first integrated circuit. I think it integrated 2 transistors, but it was nonetheless an integrated circuit. And there is no conceivable way that any human imagination could have gone from there to the World Wide Web. I mean, it's just... So here we have this sort of uninteresting looking little laboratory demonstration. Will that eventually produce something which is changing the world? My guess is not, but I don't know. I'm not putting my money into it, but that's a different issue. New materials. Here's a material that's metal. This is a ceramic, that's a plastic. And in the new expanded view of world, that's the material in a sense. What we have here is an alloy, which is gold and silver, I think. This is a mixture, an alloy of different kinds of ceramics, alumina and silica. This is a mixture of polystyrene and polybutadiene, and that's a mixture of the genes of mouse and jellyfish. And the reason that those mice are glowing so beautifully green is that it's the jellyfish gene that's expressing green fluorescent protein. And an interesting question to raise with your class ethically is it permissible to do genetic modification of animals for your amusement? That is, to make pretty animals. It's a good question, I don't know. So here is the material from which the world is made. That's a silicon boule. That's a single crystal. It goes to that. You've seen those things. That's a Bucky tube, so carbon nanotube, and here are the structures. These are just examples, pictures of pretty things. These are quantum dots, and the colors are different, interesting colors, but the reason for the different colors is that you can relate the color to the size. So if you make a structure that's the size of the wavelength of light, you can moderate that. So there are lots of interesting new materials to make there. I think that the materials that are going to be the most interesting are the ones that go into this. So here's a fuel cell. The catalysts that run a fuel cell are nanometer scale structures. This is a solar cell. The structures that run that are nanometer scale structures. This is a plasma display. Plasma displays are probably not going to make it in the marketplace right now, even though they're beautifully bright. But if you've ever seen one, you have to position it about that far off the wall because they run so hot that they set your wall on fire if you embed them in the wall. That's an undesirable result, but it also is politically incorrect in a world in which we think we have to conserve energy. Now, I don't want to go through the details here. The only point is, how does a solar cell work? You absorb light and you make what's called an exciton. And an exciton is an electron separated from the atom where it came. And then what you do is you let the electron drift around until it goes to a part of the cell in which electrons can move, but the holes cannot. And you let the hole drift around until it goes to a part of the cell where the holes can move, but the electrons cannot. And then the holes and the electrons separate. Now that's terrific. The only problem is you have to have it happen before this goes clunk and falls back together again. You get exciton annihilation. And that's about 100 nanometers.
So the critical size range for dimensions in this is nanometer scale stuff. And solar cells are not going to fix the world's energy problems, but they could well be good for 10 to 15% of solar grid, and that's a big deal. This is a fuel cell. I'm not a big fuel cell enthusiast in most cases, but the active ingredient of fuel cell is something that takes either hydrogen or oxygen and basically burns them in an electrochemical cell. You have hydrogen come in here. The hydrogen dumps out an electron. The electron goes through an external circuit. The proton that's produced diffuses through a selective membrane and then recombines over here. So a fuel cell is just basically a device for burning hydrogen and oxygen in a way in which the electrons and the protons take separate paths. And the key element to that is, again, this particle, and notice the size scale there, 2 nanometers. All right, now let me just finish things off with a couple of statements. One of the questions always that's interesting to talk about with students is, here's a new area of science or technology. What science should be done? I mean, you can do all kinds of stuff, but what should be done? And the question there is never a sort of an absolute issue of this is good or this is bad. Well, sometimes it is, but it's more often a resource allocation question. You have a limited amount of money. How do you want to spend it? My favorite case, and the one that makes me very unpopular in Cambridge these days, is research on cancer. We spend $1 gazillion on cancer. It's not leading to very much in terms of therapy. So why are we doing it? Well, you say it's a good thing to do. Of course it's a good thing to do. But is it a better thing to do than trying to figure out pharmaceuticals that would prevent Alzheimer's disease or rewire the brains of cracked babies so that they had productive lives or something like that? You can't do everything. So you have to make choices. And one of the choices here is, this is the kind of hierarchy. What should be done, what should not be done. Particularly, is nano more or less important than roads or schools or the military or tax relief? And then who decides and what are the criteria? Do we think about financial return, which is capitalism, or do we think about social return? How do we think about extending this to non-first world countries where there are big practical issues? Those are all really great questions and interesting to talk about. And one of the things to point out is that we techies like to talk about risk-benefit. Now, it turns out that most people can't understand risk-benefit. It's a really hard concept to get across. But there's actually a third dimension to this plot that everyone should keep in mind, and that's choice. So you can talk about risk and benefit, but people will choose to do something which is risky and has low benefit if they choose. And, for example, smoking cigarettes. Many people still smoke cigarettes, even though there's very little benefit and a lot of risk from doing so. Well, there actually is lots of benefit, but that's neither here nor there. So it's at least a three-dimensional axis of that sort that needs to be thought about. And here's a nice example that has a nano component to it. We have all seen the back end of a poorly adjusted diesel engine. Now, what's coming out of there is a mixture of micron size and nanometer scale particles, which we know to be, to some extent, carcinogenic. And there is a notion that we should shut down that kind of technology. On the other hand, the most efficient method, more efficient than fuel cells, for converting hydrocarbon energy into power at the axle is a diesel. They're phenomenally efficient, something like almost 55, 60%. So what do you want? You want to remove particulates, or would you like to have efficient use of fuel and less CO2 produced? Well, that's a choice, and I certainly don't have the answer, but it's interesting to work through it with students. So what are benefits? Well, I think the biggest benefit is going to be small, dense, highly portable, highly effective information systems. That I know is going to happen. So this thing is going to be able to do what your computer on your lap is doing, plus many other things. It's going to be able to talk to you and sing to you and whisper to you at night and keep you company. This is all terrific. I don't know that I like that. Benefits, electronics, the whole area of commodity infrastructure, solar cells and reverse osmosis for water, new materials of a variety of sorts, biomedicine. I mean, it really is a technology and a science which underlies many, many things. It's not the single quantum mechanical thing that physics produced in 1925. It's a technology that underlies the world very broadly as we know it, because everything that we can see has a dimension that's nanometer scale as you go from atoms to big things. So it's very broad and very interesting from that point of view. What are examples of problems to think about? The assembler is not to me a problem. You know, the idea that there's some particular malign machine that's going to crawl out of the test tube and eat the Earth. Now, that's happened before, but not in this context. So what are the problems? Here's one that I think is a very real one. In 2010, I had a quotation for this, that I could buy 15 petabits, which is 10 to the 16th bits of storage for $250,000. This price has actually gone down since then. The human genome is 10 to the 11th bits. So for a few $1 million, I can buy enough information storage to take everybody's genome planet-wide, basically, and store it. Now, for a few $1 million more, a few tens of $1 million or hundreds of millions of dollars, and I mean, we're big timers now, we toss hundreds of millions of dollars away as if it's nothing. I can also take all of your credit card records, all of your telephone records, all of your travel records, everything else about you. And by the way, the cell phone that I showed you will be telling me where you are in addition to letting me find you, so that I can build you into a web in which I know your past behavior, your genomic potential, your present position, and probably I don't have to read your mind, I can predict your future. Do we like this idea? I personally am delighted to be 67 and facing, as we say, my mortal demise at some point. I'm going to leave it up to your kids to figure this out. And then here's another one which is interesting, globalization. We're accustomed to a world, we in the US are accustomed to the world in which we're king of the hill. And what globalization has done is to make all information free and available to everyone. So now there's no competitive advantage that comes from knowing something. It's how quickly and particularly how cheaply you can exploit it. And this is a product of the information processor, and it has completely rewired the world of human beings. Now you're just beginning to see it, and you see it in terms of things like your students going out and having to look for jobs as opposed to having the jobs come to look for them. These are not small things, these are quite big things. So an interesting issue from the point of view of teaching is teaching has been based on the idea that we teach students to know things. We teach them facts, and then they go on from there. The facts are all available. I mean, I don't look up any facts anymore. I go to Wikipedia, and Wikipedia tells me not any facts, but it tells me what everybody else has decided is a fact. So we have a kind of democracy of fact. And one goes on from there, not to knowing stuff to understanding it. And so it's assume the information is free. Okay, so the summary. Nano, who cares? Will it change society? Yeah, I don't have any doubt about that. Information technology is already in progress. Energy is a central concern. Biomedicine I don't know about. Water supply, all the rest of those things, big deal. Revolutionary, science absolutely, because we can see things that we couldn't see before. The technology, I can't tell. We have fuel cells, but we're going to be able to make better fuel cells. Anyway, this is going to permeate the world of technology. Does it pose a new kind of technological threat? I don't think so. The ones that were posed at the beginning are probably not really there. And so there are issues about industrial health and safety that we have to deal with, but I personally don't think it's such a big deal. And is there something scientifically new? Absolutely. And it basically lies in these areas of structures in between atoms and molecules and materials, and in understanding the micromachines in the cell and that kind of area. Great stuff. And so I leave you to think about Mr. Columbus and the mixture of, isn't it neat to go out and see what's out there? Maybe I can make some money, and maybe people will pay more attention to me because I've done all this stuff. And you know, the whole melange of human emotions that goes into doing something new, it's all being played out here in various ways, and it's great fun to watch. So I think your students will find it interesting, and I have to say I certainly do. Thank you very much.